This is the multiple choice question. Right, the 2017 paper, this is the multiple choice question 1 to 10. Okay, question 1. All noble gases are characterised by the completion of the outermost orbital. This orbital is. Okay, so this is a little bit sneaky, but not totally. I've just pulled in the data book so that we could pull out. These are the noble gases down here. And then it's looking for what is the last orbital, or the outer orbital that you find. What you've got to remember is, this is 1s, there's 2s, 2p, so, and 3p, 4p down, all the rest of the way. So all of, from neon down, every single one of them ends with a p orbital, but helium ends with an s orbital, so it's d. I've pulled the data book again because we're looking for the electronic configuration of an atom of X and its ground state is. Okay, so here we go. 1s2. Try what's the best one to do. I'll use this. Okay, 1s2. So that's that whole of that period gone. 2s2. So that's you down up to here. 2p6 takes you to the end of here. 3s2. So we're still just rattling through the kind of top section. And 3p6 takes us to the end of argon. And then we've got 3d1 4s2. Now they can write this bit whichever way around you want to. From a filling order point of view, you go 3p6 and then you go 4s2, 3d1. But from a strictly energy level point of view, obviously put the 3's before the 4. So entirely up to you which way around you do it, you wouldn't get penalised. But if we're going, so 4s2, 3d1 we kind of take together. Here's your 4s2, takes me to here. And then I've got one of my 3ds. So I'm literally just up to scandium. Okay. Which line in the table could represent the 4 quantum numbers of an outer electron in an Mg2+ ion? So could, because there are different things. You obviously could have spins and different things like that. Okay, so let's look at magnesium. So magnesium is 282. So that means that we have, I should have maybe brought down the whole periodic table, but that means we've got 1s2, which is this one here, and then 2s2, 2p6, which gets you to 8, and then we've got 3s2 for magnesium in ground state, but it tells you it's an Mg2+ ion, so I'm going to take these out. So my outer electron is going to be in the 2p orbital set. Okay, if I was going to do this in boxes, I would say there's 1s2, 2s2, and here's my degenerate p's. So 1s2, 2s2, and, well, I've got 6 of these, but just by habit, you do the parallel and pair. Okay, right, so it's 1s2. Not that I need to write that out again, but just so you've got it, okay? Right, so we're looking for principal quantum number we're going to start with is our energy level. Our outer electrons are in energy level 2, so I'm going to get rid of D straight away. Okay, and then we're looking for our shape. And it's in the p orbital, so it's a 1. 0 would have been your S. And then we're looking for our orientation. Now, the p orbitals are either going to be given as -1, 0, or +1, because you've got 3 different orientations. So I'm to here now, because these two don't help me. And then you've got a potential spin, and the spin is either plus or minus. So any of these could have been right. So correct answer must be C. Okay. Question 4. Right. So this says the coordination number of an ionic lattice can be determined by using the following equation. We've got the radius ratio equals the radius of the positive over the radius of the negative ion. And you're asked to work out what is the coordination number in zinc 2 sulfide. So to do that, you needed to actually go looking for the radius of ions. And so therefore you had to go to your data book and find ionic radii of selected ions. Now that one's a little bit sneaky because you have to, well, you have to either know it's there or you have to have gone, well, I've got to be able to find the information somewhere. Where would it be? It could only possibly be in the data book. Okay, then you have to be able to do your, just your crossover for this. There we go. Okay, that's your zinc sulfide. And so then you've got to find them. I've clipped it just at the zinc because it's a bit long, it's a full page length. And here's my sulfide up here, okay? So literally I'm just putting that my ratio is my positive ions, so my zinc 74, divided by my sulfide ion, which is 184. That's it, okay? And when I get that, I do 0.402, goes on for a while. The important thing is that it's actually in here. So coordination number is 4. Okay, what is the formula for the diaqua tetrachlorocobaltate 2 ion? Okay, now let's break this down. Diaqua means that I've got 2 waters. Tetrachloro, so I've got 4 chlorines. So I can do something here. I can get rid of B and I can get rid of D. And then the next piece of information is I've got cobalt with a 2+. So I'm trying to work out which of these is correct. Is it 2+ or 2- on that? Right, so if I've got 2 waters, well, water has no charge, so that's a 0. 4 chlorides, that's going to be 4 times -1, because chlorine, far end, group 7, okay? So, and I've got a 2+. So 2+ -4 means that I end up with -2, okay? And why the answer is A. Question 6. Which of the following indicators is most suitable to use in a titration of dilute hydrochloric acid solution with dilute ammonia solution? Right, so this is all about your strongs and weaks. You need to know that hydrochloric is a strong acid. You need to know that ammonia is a weak base. Now, the only way that if you're struggling to remember is to look at your dissociations page, and anything which is on that page by definition has to be weak. But I would expect you to know your strong acids and strong alkalis. You know, your strong acids, hydrochloric, nitric, sulfuric, go for your kind of main ones that you've used all the time. And your strong alkalis would be your sodium hydroxide, potassium hydroxide, all them. Okay, so what happens when you do this though? If I've got a strong acid and a weak alkali, I'm going to end up with a salt that is going to be acidic. Okay, so if the salt is acidic, I need an indicator which is going to work in an acidic point. Okay, so then you're just going to go through them. So bromothymol blue, 6 to 7.6. Well, that's going shade past neutral and into alkali, so I'm not thinking that's brilliant. Phenolphthalein, definitely out because that's 8.2 to 10. Methyl orange, 3.2 to 4.4, so that's down in the acid side. So far that's the one that I'm going for. Just checking, phenol red, 6.6 to 8, so that's definitely not as good. So I'm going for C. Okay, pH of a solution of benzoic acid with concentration 0.01 mole per litre is, okay, we've given an option, right, you can see what I've pulled here. So I need to work out the pH. I'm going to use this equation from your data book. pH is a half pKa minus a half log C, because that's the information that you have. To get your pKa, I've gone from a dissociations page, and again I've just clipped the top of it so that I could get this number in here with the heading. So my pH, quite simply, and it is reasonably simple I think for a calculation on this, so it's a half times 4.2 minus a half log 0.01. Okay, calculate that out, 3.1. Okay. Oh. Question 8, you can already see what I've gone and collected from the data book on this one. A reaction must be exothermic if. Okay, so you have to look at this from a relationships point of view, and this is the relationship that you know, that delta G is equal to delta H minus T delta S. So if I rearrange that to help in how this is actually kind of related for delta H is delta G minus, plus T delta S. So I'm looking for something that would ensure, regardless of what the numbers are, that this ends up negative. Okay, because that's what I'm looking for, exothermic. And then you just work through all of them. If both delta G and delta S are negative, so if this was negative, and then I add on a T, which I'm not going to worry about, with another negative, times by negative, this would then become a negative as well. So that's a negative minus something else as well. That has to give you a negative. So it's A. If they were both positive, that definitely is not going to give you a negative. If delta G is negative, but there's no other information, well, that means that the T delta S might actually manage to cancel out, like might bring it into the positive. And delta S being positive is not going to help at all. Okay, so a little bit of maths really in that one, I think. Okay, question 9. For the reaction A plus B goes to C, following data was obtained. So we've got a rate data. This is for order. Given that the rate equation is rate equals K, B to the 2, the value of X will be. Okay, so what we've got here is that B is rate determining and it's second order. So that means if I double B, I'm going to quadruple the rate. So I've kept my A the same, but B has gone from 0.1 to 0.2. So I've doubled B to get here, which means that has to be quadrupled. And that's it. Okay, I don't think that one's too hideous. I didn't particularly like this one though. Rate equation for the reaction between nitrogen monoxide and chloride is, and you've got this, the units for the rate equation K in this reaction are, right, so this rate equation overall in order, you've got a 2 and a 1, so this is third order. So you're looking for this, but you've got to work out how you're going to know these things. I just go with memorizing it, but you can, if you wish, totally fine if you want to do the actual like calculation. So you could actually do that K, and we've got NO squared Cl2. So what you're doing is moles per litre, we're going per litre, squared multiplied by moles per litre, and and my rate is going to be in moles per litre per second. So you could rearrange all of this to work out what K is. It's a fair amount of maths, but if you're happy with it, then great. Otherwise, you just need to know that we're looking at, that's 0 order. Here's your first order, that's really what you want to be given. Here's your second, and there's your third. There is progression that you can see with the litres and the per mole. Find a way. Okay, that's the first 10.